All right, so here's the key theorem of this chapter. So we have the inverse transform theorem, and this theorem is just going to teach us how we can use random numbers to generate random variates coming from other statistical distributions. Now, the theorem is called inverse transform theorem, and it indicates the methodology of inverse transform technique, basically. So let's read the theorem. It says, let's just say x is a continuous random variable, and it has a known cumulative distribution function f. Okay, so x is a continuous random variable. Right now we are focusing on continuous random variables only. And it has a known distribution, and its CDF is defined as capital F. Then it says, if I take my random variable x and plug it into the CDF itself, the CDF function, then there will be an output. And that output, of course, is going to be between 0 and 1, right? So because we know that the CDF, the cumulative distribution function, will always yield probabilities, and all of the probabilities are between 0 and 1. So we know that the value, when you plug in any value within the CDF, will always be between 0 and 1. And if you plug a random variable x within its own CDF, in that case, the output is just going to be a standard uniform variable. First of all, when we have a random variable, if you plug in that random variable into a function, then usually the output is a random variable as well, right? The functions of random variables are usually a random variable as well. Therefore, what we expect from this R value to be a random variable as well. But this theorem indicates that if you use a random variable within its own CDF, then the output will be a standard uniform random variable. Now, we need to prove that this theorem states the correct thing. Well, how do we prove that? I mean, the theorem states that R here is standard uniform. Now, what I can do is, I can check the CDF of R by the theorem. I can try to determine the CDF of R, and if the CDF is an identity function, in that case, I will be proving that R is standard uniform. So let's just say FR, F sub R, is the theoretical distribution function of the random value here, which is not known yet. So right now the theorem states that, but we are not sure if it is really standard uniform or not. So right now we are just denoting it with FR. And what does FR indicate? It is a cumulative distribution function, which is the probability of that random value R to be less than X, right? I mean, assuming that R is also a continuous random variable, then the CDF is the probability of R being less than X. Now, I want to show that this probability is actually equal to X itself as an identity function, right? So the ultimate result here is tried to be obtained. And what I want to show that is the probability of R being less than X is actually X. So let's try to find it. So what I'm going to do is this. So we have an inequality in the probability statement, and we are going to find a solution set for this inequality for which the probability is needed to be calculated, right? Now what I'm going to do is this. I am just going to apply a monotone transformation to the both sides of this inequality, and that monotone transformation will be the inverse CDF of random variable X. Okay, so why do I choose that? Just for fun, because it is just going to bring me to the end of the proof. So I am just going to choose the inverse CDF of X, and I will apply it to both sides of this inequality. And of course, this is not going to change the probability because it's a monotone transformation. Remember, the cumulative distribution functions for continuous random variables are monotone functions, right? And they are one-to-one functions as well, so they are invertible. And the inverse of them are also monotone. And if you apply a monotone transformation in both sides of the inequality, the solution set of this inequality wouldn't be affected from that. Therefore, the probability will stay the same. So after applying this monotone inverse transformation to the both sides, then by the definition here, R is defined as the capital F of capital X, then this means capital F inverse of R is equal to X itself by the definition given in this statement. And what I can do is I can replace that F inverse R with capital X. And here I am looking for the probability of capital X to be less than F inverse of this lowercase x, that arbitrary value. Now, basically, this is a probability statement related to random variable X, which is basically calculated by the CDF of X, right? So the probability that my capital X, my random variable X, to be less than this value is the same value plugged into its CDF, right? Which is exactly this. And of course, you can easily determine here F and F inverse will cancel out, and the result will just be X, which indicates that the CDF of the random value R here is an identity function. And this indicates that if you put a continuous random variable within its own CDF, then the output will always be a standard uniform random variable. Now, this is a good theorem because according to this theorem, the opposite is also true. Now, you see, this proof implies that if you have a sequence of random variables, all of which are following the cumulative distribution function f, if you plug all of these random variables within their own CDF, then the output is just going to be a sequence of random numbers, right? So if you have a sequence of random variables which are independent and identically distributed, if you plug these random variables into their own CDF, the output will be independent and identically distributed sequence of random numbers, independent uniform random numbers between 0 and 1. So the opposite is also true. If you have a sequence of independent and identically distributed standard uniform random numbers, then when you plug these random numbers within an inverse CDF, then what you are going to get is going to be a sequence of random variates which follow that CDF. Okay, so the inverse CDF of a random variable helps us to convert random numbers into the random variates following that distribution. So the inverse transform technique is basically this. If you want to generate random variates from a specific distribution, first you need to identify its inverse CDF. Then by plugging in a sequence of random numbers into that inverse CDF, you can safely generate random variates from that distribution. So the conclusion is as follows. We can generate continuous random variates from a distribution with known inverse CDF, and we are just going to use a pseudo-random number sequence within that inverse CDF to convert them into random variates from that specified distribution. Now, what are the problems here? First of all, some distributions, they do not have any closed form CDF, such as normal distribution. So do you know a formula for the cumulative distribution function of normal distribution? Actually, there is not an existing cumulative distribution function there. So if it does not exist, how can we find its inverse? If it does not exist, if the CDF does not exist, the inverse does not exist either. So the problem is here. Maybe sometimes the inverse CDF may exist as well. However, the function may be too complicated to calculate. For example, it may consist of such numerical integral procedures. Actually, the normal CDF is something like that as well. I mean, it contains an integral of an exponential function where the power is a quadratic function in this exponential function. So it is impossible to integrate such functions. Therefore, the inverse CDF is going to be too complex to calculate there. So even though we have a solid theorem which helps us to convert random numbers into random variates from a specified distribution, what we need to have here is the inverse CDF of that probability distribution.